Hello, everyone. My name is Tyler Strauss, and I'll be speaking on behalf of BME Team 6, comprised of Cece Attwell, Joe Stuck, Alex Weber, and myself, and our project, the ball bearing temperature testing device for Stryker. Our advisors are Dr. Lee and Dr. JJ, and our project sponsor liaison is Brian Frank. Talking a little about what our project is, at the beginning of last semester, we were given a semi-functional device whose goal is to perform comparative testing between different ball bearings, which would go into various Stryker devices to see what their temperature profiles would be both over time and under load. Zooming in a little bit on the device in figure 1 on the left, we can see in figure 3 where the ball bearing itself would sit on top of the motor and directly adjacent to the temperature sensor. In figure 4, you can see a side shot of the motor which would spin the ball bearing. And in figure 5, you can see the radial and axial loads, which we applied to the ball bearing to help simulate use-like conditions. The biggest issue that we found was that the sensor itself was not the right one for the job. In figure 5, you can see a spec for the original sensor that we had. At its smallest focal point, it was 3.4 millimeters in diameter, which was far too large for the 2.1 millimeter tall ball bearings. So we ended up swapping that out for a better temperature sensor with a focal point attachment at the tip, which would reduce the focal point down to 0.8 millimeters. The next issue was actually making sure that the sensor itself was aimed at the ball bearing. The amount that it came with was static and couldn't be aimed. So we took a look at a couple different options. Figure 7 shows a purchasable micro epsilon mount, and figure 8 shows a printed mount that we were considering printing specifically for the device. In the end, we ended up choosing the purchasable option simply because we didn't know if we could maintain the accuracy that was necessary with a 3D printed mount. Here you can see the two options side by side. In my hand is the newer sensor with its appropriate mount, and on the left is the older sensor with the static mount. One of our big goals this semester was to perform a Gage R&R comparing the new and the old sensor. Unfortunately, due to the shortened semester, we were only able to get data for the old sensor, which you see here. But as is hopefully quite clear, the data is quite scattered. And as we would end up finding out, the temperature that the sensor is measuring isn't even the temperature of the ball bearing itself. It's just the static ambient air temperature in the room at that time, confirming for us that the temperature wasn't really that the old temperature sensor wasn't measuring the ball bearing, but was instead just measuring room temperature, or the far wall. Another issue that we were considering was that the motor might have been conducting heat into the ball bearing, meaning that over time the ball bearings would heat up from the motor and wouldn't give us accurate results. In figure 9 on the left, you can see a prototype for one of our heat sink options that we were considering. We did a few tests and found that at lower RPMs, a heat sink such as this one would help successfully dissipate some heat, but at higher RPMs, it has less of an effect. Still, that would be a significant benefit for the kind of accuracy that Stryker is hoping to get out of this sort of device. We are delivering with our device at the end of the semester instructions for helping improve this and also finish the Gage R&R for the newer sensor. We would like to thank Stryker for sponsoring this project, as well as our sponsor liaison, Brian Frank, the patience of our advisors, Dr. Bruce Lee and Dr. JJ, and various members of the BME staff, such as Stephen. Thank you.